For over a century, our approach to flight has relied on brute force. We build massive, heavy engines to ignite volatile chemical reactions, or we consume megawatts of electrical power to accelerate working fluids. We depend entirely on external, independent drives strapped to an airframe. This is the lenticular disc. It hovers without a traditional engine, without external combustion, and without heavy electrical power systems. If we peel back the hull, you'll see a hollow structural cavity. The craft uses this space as its energy storage medium and prop. This schematic shows the layout that makes this possible. The design is a closed, pentagonal resonant cavity, equipped with perimeter baffles and a central spiral flywheel. It takes internal acoustic vibrations and converts them directly into unidirectional airflow and aerodynamic lift. By integrating the pump and the fuel into the geometry of the hull, we bypass the need for combustible fuel. The physical dimensions of the craft govern the propulsion. The operation of the lenticular disc relies on three distinct branches of physics. First is acoustic resonator physics. We have to map out the cavity eigenmodes, the natural vibration patterns of the space, and maximize the quality factor, or Q factor, which measures how well the structure retains acoustic energy. The second pillar is acoustic rectification. This is the process of using one-way mechanical valves to force an oscillating wave of pressure into a direct, continuous stream of mass flow. The third is Coandă aerodynamics. When a fast-moving jet of fluid meets a curved surface, it naturally adheres to that curve, accelerating over the profile to create an intense low-pressure zone. These three mechanisms operate on completely different physical scales, but in this craft they are locked together by a strict set of dimensional constraints based on prime ratios. The design layers these three established mechanisms into a single closed-loop cycle, where sound becomes airflow and airflow becomes lift. Looking at this cross-section, we can map out exactly how that sequence works. Within every single acoustic half-period, fractions of a millisecond, a precise four-phase mechanical cycle takes place. When the acoustic wave causes the pressure inside the cavity to drop below the ambient air pressure outside, the one-way rubber flaps along the perimeter open. This admits a packet of external air mass into the craft. Phase 2 is compression. Rising pressure seals the flaps against the hull, preventing any outflow. The trapped air is now accelerated inward by the pressure gradient. Phase 3 is flywheel coupling. That inward rushing air strikes the spiral vanes in the center of the cavity. The air transfers its kinetic energy, depositing angular momentum directly into the flywheel. Phase 4 is vortex exhaust. As the flywheel spins up, it acts as a centrifugal pump, ejecting a rotating vortex upward through the central port. If you study electronics, you recognize this process immediately. It is a mechanical full-wave rectifier. It takes an oscillating, alternating input, the sound wave, and converts it into a direct one-way output stream of mass. The flywheel acts as a kinetic smoothing capacitor. By accumulating angular momentum across millions of these microcycles, it absorbs the rapid pulses of air and outputs a steady, continuous vortex. Once that vortex leaves the central port, it interacts with the convex upper hull. Because of the Coandă effect, the rotating jet of air snaps to the curvature of the metal, spreading outward across the surface. Bernoulli's principle dictates that as a fluid accelerates, its internal pressure drops. The accelerated boundary layer hugging the hull creates a pressure deficit directly above the craft. The total amount of lift generated depends on the effective velocity of the airflow, the surface area of the pentagonal hull, and the specific lift coefficient created by the Coandă curve. To lift a 1.3 kilogram copper hull, we calculate the balance between the weight, the disc's surface area, and air density. To reach that equilibrium, the craft must move air over the upper hull at roughly 4.6 meters per second. This required velocity translates to an internal flywheel speed of just 500 RPM, a modest rotational speed achievable through acoustic pumping. But generating that acoustic pumping requires a sustained sound wave. In a passive cavity, vibrations naturally decay. The copper hull and the internal air absorb the sound, turning it into heat. To fight that dissipation, the lenticular disc uses a solid-state piezoelectric feedback loop bonded directly to the inner surface of the upper hull. We start with the signal capture phase. A ring of 7 pickup piezos actively samples the acoustic pressure field inside the cavity. That tiny electrical signal is sent to an analog circuit. The circuit amplifies the voltage and applies a precise phase shift, timing the signal to match the exact microsecond it takes for the sound wave to complete a round trip inside the hole. Finally, 11 driver piezos pulse that amplified wave back into the physical structure, hitting the cavity precisely in rhythm with its natural resonance. When the efficiency of this loop nears 100%, the effective quality factor of the cavity approaches infinity. The system enters the phononic laser regime, where the acoustic oscillation becomes entirely self-sustaining. Because piezoelectric elements have extremely high impedance, driving them requires very little current. The feedback circuit consumes less than a single watt of electrical power. That 1 watt is not powering the lift, it is acting as a metronome. The electrical input organizes the structure of the acoustic wave, so the mechanical geometry can do the heavy lifting. If you try to build this system in a standard box, it fails immediately. The problem is modal degeneracy. When multiple resonance patterns share the same frequency inside a cavity, acoustic energy bleeds between them. Any shape built with simple dimension ratios, like 2:1 or 3:2, will cause these harmonics to overlap. The energy scatters into parasitic vibrations, destroying the Q factor and stopping the pump. To solve this, the lenticular disc relies on highly specific measurements. The hull is a pentagon with a width of 14.04 inches and a controlled depth of exactly 4.0 inches. If you calculate the natural acoustic frequency for that depth and divide it by the natural frequency of that width, you get a ratio of 3.51. That is exactly 7 divided by 2. Because 7 and 2 are prime numbers, their harmonics do not overlap until you reach extremely high orders. This prime ratio constraint prevents modal degeneracy. The energy has nowhere to leak, so it stays trapped in the exact resonant mode required to drive the flywheel. The 5-sided pentagon supports this mathematically. Its 5-fold symmetry prevents rotational waves from coupling and ensures the frequency relationships remain mathematically irrational. Pure mathematics replaces the heavy, drag-inducing external motors found in traditional propulsion. The structure itself dictates where the energy is allowed to move. This brings us to a strict thermodynamic problem. We have a 1.3 kilogram craft hovering in midair while drawing less than 1 watt of electricity. Where is the actual energy for flight coming from? The cavity is strictly an open thermodynamic system. Every time those baffles open during the rarefaction cycle, the craft pulls in ambient air from the surrounding environment. The lenticular disc functions as a reverse heat pump. Ambient air is full of thermal energy, the random, chaotic motion of molecules. As the sound wave pumps that air through the central vortex, the craft extracts that existing kinetic energy and uses it to drive the lift. The prime ratio geometry and piezos simply organize ambient chaos into coherent directed flow, a thermodynamic energy harvest enabled by the structure itself. In the 1940s, an Austrian inventor named Victor Schauberger attempted to build something very similar called the repulsine. Structurally, it shares the same DNA as the lenticular disc: closed copper cavities, rotating components with corrugated profiles, and central intake and exhaust ports. But Schauberger's prototypes faced obstacles he couldn't overcome. He used external motors to fight natural dissipation, and his corrugated disc profiles used non-prime patterns, which caused modal degeneracy. The lenticular disc corrects the math. Precise prime ratio geometry and solid-state piezos solve the energy leak that limited mid-century implosion drives. These earlier attempts failed not from a flawed vision, but from an incomplete theoretical framework regarding acoustic eigenmodes. Because this system is driven by geometry, its performance improves as it scales up. The structural weight of the perimeter walls scales linearly, but the surface area, and therefore the lift capacity of the Coandă curve, scales with the square of the radius. Due to this square-cube relationship, larger lenticular discs inherently capture more ambient air and pump more mass, making them easier to fly. Future development will focus on validating these curves through simulations and replacing the passive rubber flaps with active electronic microvalves for higher efficiency. The lenticular disc relies entirely on established physics, demonstrating that advanced propulsion can be achieved through pure geometric and acoustic constraint.